Hi guys, welcome back to Data Every Day. Today we are looking at a data set of houses in Poland and trying to predict the price of a given house. So house price prediction is quite a common task of machine learning, but we're going to do another one. Just going to try to predict the price column right here based on the rest of the features. So let's hop into the notebook. We're going to use pipeline for this. So I'm importing first NumPy and pandas for working with the data, and then from sklearn I'm getting train test split for pre-processing, and then all of these will be part of our pipeline, including the final model, which will be a gradient boosting regressor. So let's go ahead and import all of that and load in the data using pandas.read.csv. We can grab the file path, the CSV file up here. I'm going to copy that and I'll paste it in, and we can have a look. We actually got a problem, and that's coming from these characters over here. So we need to specify an encoding in here, and usually the Latin 1 encoding works. So let's, there we go. We now get, so I'm not sure if those are the right characters, but it doesn't really matter. We're not going to really use this column anyway. So let's look at some information about the dataset. And we have no missing values. Two object columns, which would be these two, the address and city. Now it would drop the address and we'll keep the city. The reason is address will be always unique, which means it doesn't provide anything useful to the prediction. And as well, ID will also be always unique, and the unnamed 0 column, that's just a duplicate index column. So all three of those we're going to drop: ID, address, and this first unnamed column. So let's go pre-processing. And this will just be the initial pre-processing that we do before the pipeline. I'm going to create a function called preprocess inputs that's going to take in a data frame. For now, all it will do is copy over the data frame and return the copy. So I'll store the processed copy in X and pass in data as our input to the function. X will be just to copy the data, but this is the copy we'll perform our pre-processing on. So the first thing I'd like to do is just drop those columns. Unnamed 0, address, and ID. We can do that with df equals df.drop, and then in a list, just put them here. So we have ID on the end, and then unnamed 0 and address. And we're going to drop from axis 1, which is the column axis. Just say drop unused columns. I must have, yeah, there's a tab there. Okay. Alright, so this is our data set. So it looks like the city will need to be one-hot encoded, because I can see at least 3 values in there. That's 1, 2, and 3. And there's no ordering between the values. So that's definitely one-hot encoding. I don't even have to do any further investigation. Everything else is numeric, continuous variables. This is the number of floors, the number of rooms, and then everything else, I think this is square footage. Let's actually double check that. SQ is number of square meters. Okay, square meters, year. These are all numeric features. They don't need to be touched. Basically, all we have to do is now one-hot encode the city column, scale the data, and then make predictions. So I'm doing that with my pipeline. The reason you use pipeline is you allow the user to enter. If you're using this model in production, you can allow the user to enter their city, like actually typing in a name, instead of knowing the city code, or because after we one-hot encode and scale, the city values become really just sort of scrambled numbers, and you can't expect the user to know what that means. If you want to be able to input human readable inputs, you use pipeline, and the pipeline will take the human readable inputs and automatically perform the transformations and then make predictions on it. So first, in our function, we'll split the data frame into X and Y. Y is going to be just the price column, which is what we're trying to predict. And then X is all the rest of the data. So we'll drop price from axis 1, store that in X. And then I guess we'll do the train test split in here. So we'll split this split the data set into 4 new sets of the data, which will be X train, X test, Y train, and Y test. And we'll use the train test split function from sklearn for that. We just pass in X and Y, specify a train size. Let's do 70%. Keep shuffle equals true. And a random state. to ensure the shuffle is always done the same way. So the shuffle will happen first, and then it will split the data, and so this will ensure we can duplicate the results. Now let's return these 4 sets of the data down here and get them back over here. And let's look at xtrain. So xtrain just doesn't have the price column, and it's 70% of the original data. Alright, ytrain should be our target values, which are the price of a given house. Now let's build the pipeline. Okay, so we only need 3 steps in our pipeline. One will be the one-hot encoding, one will be the scaling, and one will be the model. So let's do that here. I'll create the pipeline. Actually, I'll just call it model. That will be a pipeline object from sklearn, and the pipeline takes in a certain number of steps. Each step should be a tuple with a name and the actual object that is used. Whatever object you pass in here has to have a fit and transform function, except the last object, which will be the model, which should have a fit and predict function. And I think a score function as well. Okay, so the first thing is going to be our preprocessor. So let's call it preprocessor. And we don't have it yet, so we can't put it in. But after that will be our scaler, and for that we're going to use a standard scaler, which will give each column a mean of 0 and a variance of 1. And that will improve the performance of our model. You know, actually, I'm not sure it will improve the performance because we're using a tree-based model here, which is gradient boosting. That's using gradient boosted trees. And tree-based models are actually not affected by scaling. However, it's still good practice to use a scaler, and it's not going to reduce the performance of the model, so we'll do it anyway. And that would also allow us to substitute the model for any other model and still achieve good results. And then last, we'll have our regressor. And the regressor is a gradient boosting regressor from sklearn. Alright, so now we just have to put in the preprocessor. So the preprocessor is an object. We're going to use the column transformer, and basically what that does is it takes a transform, and we specify which columns we'd like to apply the transform to, and then it'll do it for us. Now, before we specify the transformer within the column transformer, we need to actually create sort of a sub-pipeline to be used within the column transformer. So this is our one-hot transformer, essentially. I'll call it nominal transformer, since we're using it on a nominal column. And this is going to be a pipeline, except its steps is just going to be a single step called one-hot. And it's going to be a one-hot encoder from sklearn. I'm going to include sparse equals false in there so that we don't have a sparse output. And now this is the transformer we want to specify in our column transformer. So let's go ahead and make that here. And the column transformer is going to be our preprocessor. So the column transformer takes in a list of transformers. If you were doing ordinal encoding, you would put these in also. We're just doing one, which is the one-hot, and I'll call this nominal. And the transformer here is the nominal transformer we just created. And then we specify the columns we want to apply this to. So there's only one, which is city. That's the column we want to one-hot encode. So I'll put city in there. And so here we create the one-hot encoder. Here we say, okay, use the one-hot encoder on the city column. And then in here, we just put this right in to our pipeline. And this should be it. The one thing I should point out is in the preprocessor, we want to make sure that we include remainder equals pass-through. Because otherwise, the columns that aren't one-hot encoded or aren't touched by the column transformer will be dropped from the data. So pass-through allows them to pass through along with the transformed columns. Alright, we'll run this. That's our model. Now we'll do training. And this is now just one line, model.fit xtrain ytrain. And you can see, so we've passed in text data, essentially, like the city column. And it automatically performed the one-hot encoding on it, scaled the whole data set, and then fit it to the gradient boosting regressor. So let's get the results. Alright, so first let's get the RMSE. So I'll create some predictions. This will be model.predict on xtest. And so what this looks like is just the predictions for each value. Now ytest is the actual predictions. And if we can get the RMSE, which is a root mean squared error, by first taking the error, which would be ytest minus ypred, the difference between the two, and so that's element-wise subtraction from ytest and ypred. Then we square the differences, and that will have the effect of removing any negatives, putting them all on the positive scale. And then after we square them, we take the mean, numpy.mean, so we get the average squared error, and then we take the square root of this. And the reason we take the square root is because when you square it, you're moving out of the original unit of the target. So here, I'm not sure what currency it's in PLN. Let me look up what is PLN. I'm not sure. Okay, it's zloty or something. I'm not sure how to pronounce this, but this is the currency we are using. However, if we square it, we're then using the squared unit of the currency. So by square rooting again, we return it to its original unit, and you can see this is the average error across all examples. So on average, we're off the prediction by about 245,944 of the Polish currency. And let's call that RMSE. So this isn't so great. I wouldn't say it's fantastic. But you look, some of these are quite high. Like this is 1.47 million. So maybe this isn't terrible, but you know, I really wouldn't. This isn't ideal. So that's RMSE. Let's just print it out. RMSE. And we'll display it to 5 decimal places, and we'll put into the format. We'll input RMSE, and then we can see it. Okay. So now we'll do the R-squared score. And R-squared score is a measure of how much better our model is than the baseline model or null model. The baseline model is the best model we can produce when we only have access to the target values. So if we don't have any access to any features, if we don't have xtest, what's the best thing we can do with just looking at this? Well, the mean. The mean would be the best guess across all examples that would reduce the error the most. So here is our baseline estimate. What that means is we guess mean for every single example. That would be the baseline model. So we can get the RMSE of the, well, actually I'll just do MSE. The MSE of the, no, it's not going to be mean. It's going to be the sum of squared errors of the baseline model. So this is the prediction for the baseline model. So if we do ytest minus the prediction, these will be the predictions that these will be the errors for each baseline prediction. If we then square them and sum them with numpy.sum, we get the sum of squared errors for the baseline model. If we do the same thing for our model, that would be ytest minus ypred, and we square this. So this is the errors for our model. If we square this, we get the square errors for our model. We take the sum, that will be the sum of squared errors for our model. Now, the percent, well, the difference in, well, let me just show you the formula. Let's call this one baseline errors. And we'll call this one model errors. put them together. The formula for r squared is 1 minus model errors over baseline errors. And this should have parentheses around this part. So this is a fraction in here. And what this formula does, let's look at it. Run that. I misspelled it. Oh, there we go. Alright, so it's a 0.7859 r squared. So that's fairly okay. It's saying we're doing much better than the original baseline model. But you can see the formula makes sense, because what this the baseline errors always stays the same. We can't change that because our targets are already predefined. The model errors is all that changes. So if we have a really low model error, the lowest it can be is 0, then this whole thing goes to 0, and 1 minus 0 is 1, and that would be an r squared of 1. On the other hand, this can be really big, let's say some crazy big number, then this whole thing goes to 0, and goes to a very high number, not 0. It gets really big, and 1 minus a really big number is a negative number. So r squared on the lower end has no bound. It can go deep into the negatives. So it's really a measure of how better your model is than the baseline model. And we'll call that R2, and I'll print it out. R squared score. We'll display it to 5 decimal places and format with R2. And we can just confirm that this is the r squared score by checking sklearn's r squared score with models.score, xtest, ytest, and it should be exactly the same. So yeah, there you go. So yeah, that will sum up today's video. Thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.